Hello and welcome to Watch This Space with Rivada Space Networks. I'm Brian Carney and my guest today is Konrad Nieradka, and we're here to talk about what a gatewayless orbital network means. Konrad, welcome to the show.
Hey, Brian. Thanks for having me.
It's a pleasure. As I mentioned, I wanted to ask you today about what a gatewayless constellation means, but let's back up one step, and can you just explain for us what is a gateway and what is its role in a satellite constellation so that we understand what it means not to have one, maybe?
Sure. So gateway, as the name suggests, is a gate through which you are accessing something else. It can be a gate into somebody's house. It can be a gate into a garden. In networking terms, a gateway is the way to either enter or leave a network. If you have your own Wi-Fi at home, you will be having several devices on this Wi-Fi. There will be at some point a router that will take you to your provider that will give you a gateway to the internet. So that's your gate to the broader internet. The satellites also used gateways since the beginning of their operations. Gateways were there to allow remote users access other networks through the satellite. And it was a typical way of doing this because it was simpler. When the technology wasn't as sophisticated as it is today, it was much easier to centralize the control of the network and bring the users through the satellite to a hub and then open a gateway either to the internet or to the broader or to the corporate network.
Okay, so how is the outer net, how is what Rivada is building different from that?
Well, we are the first gateway-less network. There were some gateway-less type of networks in the past. They were less popular. They were mostly closed networks, mostly used by the military. VSAT mesh networks, for example, they were popular at some point. But in the commercial world, everything is going through a gateway still. We are building something that will allow the users to connect, we can say, from rooftop to rooftop or from a ship to a ship without having to go to any other hub in any other country to control this link, to get a gateway to some other place. And we are doing this because we are offering not internet access like most of the satellite operators, but we are offering a truly private network. We are not connecting consumers, we are connecting enterprises and governments, and we are not connecting them to the internet or to any public network, but we are allowing them to link their offices in different countries, their ships, their airplanes, link them together in a very secure way where all the data still belongs to them and doesn't traverse any third-party networks.
Okay, let me just make sure I understand that, because I think a lot of people, they imagine that, when you connect to a satellite, that satellite, you're talking to that satellite, and that satellite is talking directly to whatever the endpoint is. But what you're describing is that's not exactly right. That most of the time, what we do is we go up. One of my earlier guests called it, kind of a mirror in the sky, right? You go up to the satellite, and you bounce straight back down to this gateway, and then from there it travels the same kind of data path that any terrestrial network would to its final destination or to the public internet or some server somewhere or whatever. And when we say we're gatewayless, what you mean is we go up and we go across this orbital network with laser connections, right? And then straight back down to whatever the final point is. And other people don't do that. Is that fair?
That is correct. If you think about a real-life application, you are on a ship heading for the port of Cape Town in South Africa, and you need to contact your offices there to prepare for the customs work, and you have a satellite connection, and you try to connect there. Most of the time, your connection will go somewhere else. It might land in Kenya, and then use terrestrial networks to get to South Africa and to that specific office, because maybe this provider doesn't have a gateway in South Africa, or because their network works better for their operations if they land this connection in Kenya and not in South Africa. And then you end up going through a lot of other networks in different countries provided by different operators. And it is either very difficult or plainly impossible to ensure full sovereignty of this data. You don't know if somebody is not listening, and to ensure quality of service. So if your application is sensitive to latency variation, or to the bandwidth that is allocated to your service, it's almost impossible to ensure this when you traverse multiple public networks. With our system, you are able to get the signal from your ship to the satellite and land it directly at your office. And that's on the short route. But you could have the same situation when you want to connect to your shipping company back in your home port in Auckland, in New Zealand. Maybe you would normally use a gateway in Kenya and then go through the fiber under the Indian Ocean to reach Australia, and then other fiber to reach New Zealand. With our system, you will just go up, you will go across the intersatellite links with the speed of light and land at your office in New Zealand.
Okay. So you gave the example of shipping a couple of times. Are there other applications or other kind of use cases that you think are particularly benefit from this type of architecture? Who are the outer net's kind of ideal users, if such a thing exists?
The ideal users are those who for whom security and quality of service create a lot of value. As you discussed with your previous guest, we are not at the race to the bottom on price to offer the cheapest possible service. We are trying to provide the highest possible quality and security. So this would cater to people for whom that is really important, because the value in their mission is created through security and through quality of service. In the realm of security, yeah?
Yeah. No, go on.
In the realm of security, you can think about knowledge-based industries, big pharmaceuticals, oil and gas, when the information transmitted between different offices in different regions, between oil rigs and so on, has huge commercial value. And it's not only important that this information reaches the other end on time, but also that it's not corrupted or intercepted. It's important for financial institutions, for stock markets, for traders. And then another aspect is quality of service. When your application requires, for example, control of latency and assured bandwidth. Let's say you are having a mine in the middle of Chilean desert. You might have operators on those excavators in that mine being on site, but then you have to train them for the harsh conditions there. They will probably get additional hazard pay and being away from the family for months at a time, and so on. You have to move them. You have to house them. You have to cater them to them at that site, which all is cost and safety issues and so on. But what if this worker can stay safely in Santiago, Chile, and work from home, operating that excavator, because you can provide low latency connection that gives him 360 view of the environment, all the telemetry from the machine, and allows him to control this with very responsive way, so that he immediately feels on his controls how the machine reacts. And this kind of operations can be also enabled by system like ours.
That's cool. Is there also a coverage benefit? I imagine that if you have a gateway-bound system, your coverage might be limited if you are not within range of one of those gateways. So being out on the high seas, for example, or you just mentioned sort of the high desert, there might not be a gateway nearby. Is that another advantage of this this architecture?
It is, and it becomes much more difficult to provide coverage when you don't have inter-satellite links, because in that case, the satellite has to see both the user and the gateway. This limits your coverage by the deployment of the gateways, and these systems become very expensive to deploy and to operate because of the footprint of the ground segment. You need antennas in every single country, sometimes several antennas per country. Then you need to get service from terrestrial networks to connect that to the public networks, to maybe create a private interconnect. The costs pile up. Once you add inter-satellite links, you can get away with coverage to some extent. You can still provide service in the Arctic or over the oceans, as long as your satellites fly over them. But then your gateways become bottlenecks, because then even more traffic is sent to those few gateways. So that solves to some extent one problem, but creates another. With a gatewayless system that is in polar orbits, we have the benefits of the ISLs, we have the benefits of global coverage, and we are not constrained by any gateways. So any user can land the traffic directly where the traffic is needed.
Okay, that makes sense. But I imagine, though, that to design a system that can backhaul all of that traffic, within the constellation, it's a different kind of set of calculations, right, than if you were just trying to offload all that data as soon as possible. That you have to design the whole system to carry more data. So are there implications in terms of, is it the complexity of the satellites or power demand? How simple would it be, is part of what I'm asking, to just add inter-satellite links and say, okay, now I've got an outer net too.
Very good point. Anybody can ask, okay, can others do the same thing? Can they replicate this? Can they upgrade their current systems to do the same thing? And the answer is, well, they would have to copy everything that we do. So basically start from scratch and build yet another system. Our system flies at a bit higher altitude, and
Okay.
because of that, we require fewer satellites to cover the entire globe. We don't have thousands of satellites, we have hundreds. And then we can afford to make those satellites a bit smarter. They're a bit heavier, but they're also a bit smarter. So these satellites will be able to understand what kind of traffic they're receiving, who is the destination of this traffic, and manage this traffic accordingly. But of course, there are limits to the compute and the memory capacity you can put in a satellite. It's much more expensive than on the Earth because of radiation, because of the power requirement, and so on. So there's yet another benefit of having the inter-satellite links and having a gatewayless system. We can control the entire system from a single brain on the Earth. And this brain can see everything that is happening. Of course, not the user data, but the traffic patterns, who needs to move what where. And this brain can compute those paths in a way that offloads the complexity from the satellites. Satellites are closest to the action, so they will be doing the things that are time sensitive and that do not require the big picture knowledge of what's happening everywhere else. But the central brain will be able to orchestrate the entire constellation, manage the power level of all the satellites, and define the rules of engagement, so to say, for the satellites, how they should handle the traffic in the best possible way.
Okay, that makes sense. I have another technical question that I'm hoping you can explain to me in a way that somebody like me can understand, which is I've heard it said by our engineers that we're operating at kind of layer 2 of the network stack, and that other constellations are at layer 3 at the TCP/IP layer. And can you just explain to me what that means, and again, maybe what the significance is for the Outer users?
Sure. As I mentioned before, we are building a private network. The difference between these layer 2, layer 3 protocols is like the difference between private networks and the public networks, or your local area network at home or the office, and the broad internet. So layer 2 is Ethernet, something that was created for connecting computers in one building at the beginning.
Okay.
And layer 3 is IP, Internet Protocol, that was created to connect different networks together, between link a network in Stanford to the network at MIT, for example. And this gave birth later to the internet as we know it. When you are working on the IP level, that's usually when you have to connect computers that are, or computer or devices that are in different organizations on different continents, usually crossing the internet. When you are going to a website, that's where most of the time is the default protocol for you is the IP protocol. But if you are inside of an organization, IP is still used there, but you can start on a lower level, on the Ethernet level. And that's what was happening in the late 90s and early 2000s. People started to build bigger local area networks, first connecting different buildings together into a campus network, then maybe connecting different campuses across the city, creating a metro network, then regional networks. And then they try to build a network that would span maybe continents. The problem is the providers of those connections between these local area networks are usually national or regional telco operators, and they have a limited terrestrial footprint. So if you want to connect an office in New York to an office in Berlin, you probably have to go through 3 different operators that have to peer together, create a connection for you, and then make you feel like home, either whether you are in New York or in Berlin. With our system, since we are also working on the layer 2 Ethernet layer, we can now bring this home network experience to the enterprises globally. You don't have multiple operators in between anymore. You start in New York, you go to our satellites, cross the Atlantic, land in Berlin, and these 2 local area networks are now joined together. So you can click print my email in New York, and it's being printed in Berlin if that's what you needed this for. But it mostly will be used for more advanced applications than that, for moving critical data between those sites, for securely video conferencing between these sites, and so on.
Sure, but now those sites on different continents can be networked as if they are in the same building, so to speak. So that's
yes.
You're not going outside and through the public internet and then having to tunnel back into some secure thing on the other end. You're kind of creating, as you put it, sort of your single domain, your single building, using our network and bypassing all of that, the TCP/IP stuff in between.
That is correct. And there are ways to emulate this with current technology. There are IP VPNs. You can buy such a service to connect even through the public internet from New York to Berlin and have an encrypted, to some extent secured connection. But there are things you cannot assure there, like the latency of that connection or the bandwidth. That you are competing with everybody else. And internet, per definition, is a democratic medium. So nobody can pay additional at a priority or to reserve resources. So that's where it's limited. And there are applications that need this assurance of bandwidth and assurance of quality of service. That's where the private network play. And that's where our homogeneous global network becomes better on long distance than an aggregate of 3 or 4 private networks from local telcos.
All right, thank you very much, Konrad. That's fascinating stuff, and I'm sure we will have an opportunity to talk again. But I appreciate you giving us your time, and we'll talk soon. Thank you. And thank you all for listening. This has been Watch This Space with Rivada Space Networks. I'm Brian Carney.
Thanks,
See you
Brian.
next time. Thank you. Bye.